Good morning, everyone. Again, thank you for joining us on today's webinar about Vilink breaking speed barriers using 3D printed injection mold printed on a 3D Systems ProJet 3500 HD Max 3D printer. I'd like to introduce our speakers today. We have three folks on the line. Myself, Tom Sharon. I am the VP of Product Marketing for 3D Systems. And I'm very happy to have Ray Zaganto, the president of Vilink, with us, one of our customers, and also Frank Zaberna, who is the R&D director at Vilink. And the three of us today are going to take you through a brief presentation, and then we'll be opening it up to live question and answer. So let me start with a quick introduction to who 3D Systems is. We're the company that makes the 3D printer and the materials that Vilink is using in this particular example. And we're known for providing the most advanced and comprehensive 3D digital design and fabrication solutions. And we're really proud of our leadership through innovation and technology. 3D Systems invented 3D printing with stereolithography that was actually invented in 1983 and first commercialized in 1989 by our founder, Chuck Hull. We also invented selective laser sintering, more popularly known as SLS printing, and we were the first to commercialize it in 1992. We invented the color jet printing process and commercialized that in 1994. And we invented multi-jet printing, which is the technology behind the ProJet 3500 that we'll be talking about today. 3D Systems is unique in that we provide by far the broadest array of 3D printing solutions available on the market. Everything from printers that sit in your living room or your garage, in children's classrooms, all the way through to your office and onto the factory floor. And we have systems that cost less than $1,000 all the way up to more than $1 million. And of course, you know, a broad array of materials that you can print in, accuracies, speeds, color or no color, single material or multi-material. There's a vast array of different options that we offer in a variety of different printers. And as we look at how companies are using 3D printing today, particularly in the manufacturing realm, we can group the different types of applications into 5 broad categories. And if we start from the left, sort of the earliest part of the product development process is really all about printing models for communication purposes. So these are 3D printed parts where there's an emphasis on the aesthetics and the appearance of the parts, and it's all about communicating your ideas. And we all know that it's much better to hand a prospective customer or a decision maker inside your company a model that they can hold in their hand and look at and really understand a product idea rather than looking on a screen or looking at something on a piece of paper. So that's what communication models are all about. The next step in the phase is prototyping. And this is really about functional prototyping or validating various engineering ideas. And here you want prints that are precise. You want prints that can approximate the function, fit, and form of the product that you're designing so that you can test and validate your ideas. The next step, which is the one we're going to be talking about today, is tooling and rapid tooling. And this is all about getting to production very quickly. And I'm not going to talk a lot about this because we're going to cover this throughout the presentation. 3D printers can also make direct end-use parts. We can make parts in metal, a variety of different plastics. We can even make parts not for manufacturing, but more for fun in food. There are edible 3D printers, and 3D Systems is coming out with a printer for edibles in the not-too-distant future. And the last broad category really ties back to healthcare, but some other areas as well, and that is mass customization. And the idea here is you can print millions of individual parts, and there's no additional cost associated with having every single part that you create be slightly different. And this is a huge advantage of 3D printing. Okay, with that, I'm going to hand it over to Ray, and he's going to talk to you a little bit about who BuyLink is, why they're using 3D printing, and what they've been doing with the Project 3500. Ray?
Thank you, Tom. Good morning, good afternoon, everyone. We appreciate this opportunity. About BuyLink, what we do, we're a high-volume manufacturer of complex metal and plastic components and electromechanical assemblies. If you think about products or sub-assemblies that are about the size of a laptop computer and smaller, stamping through 600 tons, injection molding through 500 tons, and vertical insert molding through about 350 tons. So that gives you a sense of what we do. We're an international player, factories in the U.S., Mexico, and China. So why are we so interested in prototypes and pre-production? Well, you know, here it is in a nutshell. We've been doing this for 53 years across demanding industries for the very best and the biggest OEMs around the world. The lessons that we've learned very early is that the projects that launch the best, run the best, and have the best economics are the ones that we're able to get involved in early. We need to be able to influence a design to improve the manufacturability. High volume metal and plastic manufacturing, it's tooling intensive. It still is, and we're experts in tooling, and that matters. Our biggest impact happens when we engage engineer to engineer. This year, we rolled out the Hardware Store by BuyLink. It's a place for engineers, by engineers, to collaborate with our technical staff, get access to our technology and resources. It's a place to test, talk, tinker. What we intend it to be is an extension of your model shop with a whole bunch of global manufacturing horsepower backing it up. Part of what we do in these spaces, we have one in Raleigh, North Carolina. We've got one opening in San Diego very shortly, is we host events for our customers. We want it to be a place, an extension of our customers, of their model shop. We want our clients to be able to come in, attend events. The Midnight Lunch Lab that we referenced there is really a nod to Thomas Edison. From our perspective, he's a master at bringing together teams of people with diverse backgrounds to define and solve really big, important, worthwhile problems. And we look at this space as somewhere where we can work with our clients, engineer to engineer, to solve important problems. The opportunity, as we saw it, a couple of years ago, it really became clear to us that our customers required our industry to do more faster. Improvement needed to happen by an order of magnitude, not incrementally. The process needed to happen in days, not weeks. DFM, design for manufacturability, needed to happen in real time at every step. Speed and flexibility were a given to accommodate changes. So the goal, as we saw it, was how can we get our customers a few parts per print in the material of choice that confirms form, fit, and function now, not later. So how do we get here? Tom said it earlier that with additive manufacturing, complexity is free. In our industry, tooling is complex. By extension, additive manufacturing is at least a part of the solution. we learned that it's more than that. We did some research, saw that printed molds had been attempted, but it never really seemed to evolve. We've all seen the same video of the high-impact polystyrene spoon being molded or the impeller, but nothing seemed to change. We placed a small initial bet. We bought one of the $1,000 printers and just started experimenting. Bought some extra reels of PLA and started to play. We come from a long line of tinkerers, as I'm sure many of you on the call do as well. We discovered that the process, additive manufacturing, it had its benefits, had its quirks, had its limitations, continued to research processes and materials, and ultimately chose our next platform to be the 3dsystems HD 3500 Max to begin our testing and our experimentation for printed injection mold tooling. And we learned some interesting things, contrary to what we thought going into it. Number one, printed molds can take the heat. It's not something that's just relegated to polyolefin type materials, lower temperature thermoplastics. Compression is your friend. The materials are compression friendly, and that's not a problem. We discovered that the molds can be toughened through a post-processing process that we've developed. The longest mold print that we've had to date is about 12 hours, and that's based on Z height. And in the course of that 12 hours, we actually printed 2 sets of tools. So it's been a very it's certainly given us the speed compression that we needed. Production quantities that we see from printed tooling, it's anywhere from typically from 5 to 200 pieces that we're able to get in the customer specified material, and the quantity of pieces is really dependent on the type of material, geometry, and complexity of the tool. We're molding parts with undercuts, with vertical shutoffs, and as you'll see, we're even doing insert molded tooling as well. At the end of the day, what it really did is allows engineers and designers to iterate in hours, in days, in the actual production intent materials. So where we've gone from here, we currently have 3 3500s in the company and expect to be adding more to help us grow this part of our business as well. So that's the quick tour of how we got where we are right now. And now I'll turn it over to Frank to share with you some of the examples and the applications that we've done.
Yeah, we have a few examples. Some of the parts, this is Frank, our R&D director. Some of the parts we've done, what you could see with ours is we're doing basically any material that we shoot in production, we're running through these printed molds. All right, this is an example of a part we did with LCP. We injected at 650 degrees into a printed plastic mold, and you can see that part's pretty long. It had some thin sections in it. Okay, down on the tail of it, the thickness was down in the 0.6 range metric, so it took a lot of pressure to fill that part, 6 inches long. You could see where we injected, and it wasn't a problem. Most of what we're doing is pre-production validation testing, so most of our orders tend to be 10 to 20 pieces. They're not real high, so these were a perfect solution. We get parts that are exactly to print. These went into medical assemblies that they used for validation testing. They weren't just visual samples. These actually work. These help print tolerances. We could do core pins, undercuts, slots. It's been very helpful to us. We've been doing it now about 2 years. This, the next part. This one here kind of highlighted how quickly things could evolve when you're using these machines. This was an actual part we did for a customer. It's a cover that goes into a housing. Their normal cycle time for a part like this was a TPE, I think it's saying 45 thermometer. Their normal turn was in the 2 to 3 week range for prototype tooling. Okay, we did 4 spins on this part in 6 days, and then including FedEx to the customer. They would send me parts in the afternoon. We'd design a mold, print it overnight, mold parts in the morning, and ship them again. So what it did was took their development time that would have been in the 3-month range and brought it down to a week. and this was actual parts. They functioned. We ran, each turn was in the 25 to 50 parts, so it was a perfect answer. It's hard to see in the pictures, but there is actually, one of the advantages you get with the 3D molds is sometimes you could actually create features in these molds that would be impossible to machine. You could actually print underneath the surface of the mold, especially with these elastomers. So you could twist the part to come out, but instead of having to put slides in there, we were able to print hollow areas and inject into them. You could see our thicknesses. This one, the minimum thickness was about 0.5 millimeter. We do thinner. It just depends on the part, but this one also, what you find with this material is thermally, it's neutral. It doesn't absorb a lot of heat. It doesn't take it away. It doesn't store it. It's just neutral. So flatness on the parts is actually really easy to maintain because they cool so slowly. Then you could actually use it to help with the sink too. The first part was a real good example. As long as that one was, we were able to easily inject it with this material, where if you had been in a metal mold, you'd be heating it and everything else, which in a prototype, you know, where you're going to make 10 or 12 pieces, gets a little involved. Here, with the material being neutral, we could shoot it in there 6 inches long and not cool the material while it's injecting, so we get a lot better flow. This is an example of one of the insert molded parts we did. The little contacts were 0.15 thick. It was an actual part that was going to go into production, but for pre-production samples, you can see here, to make the mold with the gauging in it for the metal inserts and everything was about a day. So, you know, it took the lead time from what would have traditionally printed probably about 2 weeks. I mean, we could ship parts in 1 or 2 days. And that located the inserts. The part was actually the same exact material, same exact size, same exact construction as what they were going to use in production, but we could turn it in a matter of days. We didn't do a real high number. You could see how tall some of those features were that had to go down inside the mold. But we got 25, 50 parts out of it, which was, for a prototype order, was more than enough. None of these molds tend to be very high volume. It's not what we're using it for. If we get an order for 1,000 pieces or something, we'll go into a different kind of mold. These are intended for very quick turn pre-production parts that need to be right on the button. They're print tolerance, they're the proper material. You just can't use a printed sample because of the properties of the material. We get the accuracy on the printed samples, but you don't get the same characteristics in the material. That's where these shine.
All right, let me tell you a little bit about the Project 3500 series plastic printers. As we've been talking about, Bilink is using the Project 3500 HD Max, which is the top end of the 3500 series. There are several printers available. But these printers are all about printing functional plastic parts in high definition right in your office environment. Project 3500s, and I mentioned earlier that the underlying technology that's used in this printer to print is called multi-jet printing, or MJP for short. And MJP really makes beautiful functional parts in a variety of different materials. And you can see, as we know, these parts are tough. They're tough enough for printed injection molds. They're also tough enough to be hydroforming molds, and you can see in the upper left-hand corner the underlying mold that you can see there, and a formed piece of sheet metal that has been hydroformed over that mold. So very high pressure resistance, very high impact resistance on these materials. There's white ABS plastic-like materials that approximates ABS plastic. There's clear materials. There's black materials, and several others, and I'm gonna touch on those a little later on. Again, the Project 3500 is all about having very, very fine detail resolution. So you can see some of these parts here as small as a US dime, the level of detail that you can get. This Buddha statue that you see over on the left, just to give you an idea, that's just a few centimeters tall. So that's a very small part, but the detail on it is just exceptional. And the material that's printed in is beautiful, as you can see. One of the things that MJP technology from 3D Systems is particularly good at is consistently sharp edges and corners. So you can see we've taken very close-in shots of some plastic parts that have been printed on a Project 3500, and you can see the very fine detail. So like a speaker grill mesh or this electrical connector, the edges on that connector are very, very sharp, very crisp. And that's not something that you see in all 3D printers. Some printers, in fact, struggle with this quite a bit. And sharp edges and corners are not just about aesthetics. As we know, there's really big fit implications and even form and function implications to having sharp edges. You can imagine that if you print a mold, that you want that parting line to seal in very tightly so that you don't get flash. And this is another area where using the Project 3500 has a significant advantage because of the sharpness of the edges that come out of these prints. And it's not just about the edge sharpness and the surface smoothness, which are excellent from this printer. It's also about accuracy and precision and repeatability. And the prints that come off the Project 3500 are accurate enough for all kinds of applications, including snap fits, assembling parts together. You can mix and match printed parts with other molded parts and other formed parts, whatever they might be. You can assemble everything together for prototyping, for low-run production use. And the parts that come off of the Project 3500 are pretty tough. In fact, they're tough enough, obviously to do the injection molds that we're talking about today. And you can see the shot on the right is another one of the molds that BiLink has created, and the parts that came off that mold below it. On the left is an example of printing an end-use part for a very tough and challenging environment, which is race cars. So this is Nissan Motorsports in Australia. They're V8 supercars, which are essentially similar to NASCAR in the U.S. They're V8 supercars. They run these in very high temperature environments out in the desert in the summer. And to keep the drivers cool inside of the vehicles, they have special cooling systems. And the part that you see, the black part, is printed on a Project 3500. And that's a blower motor assembly that's custom made and is run on those race cars in races and stands up to all of the temperature, vibration, and other issues that would be present in a racing situation. And that's directly off the printer. So these parts can be pretty tough. And I mentioned earlier that the Project 3500 offers a variety of different materials. I'm not going to go into a lot of detail here. We have information on the 3D Systems website about each of these materials in particular. But just to point out quickly, the material that is being used by BiLink to print molds is VisiJet M3X, which is a white material that gives an injection molded plastic look and feel if you're printing end-use parts. It's got ABS-like performance, and obviously it's tough enough to stand up to everything that Frank was describing in terms of temperature and pressure and that sort of thing. We have materials that are USP Class 6 capable for medical applications. We have clear materials And we even have castable material so that you can print a sacrificial pattern on the Project 3500 and then cast that as a metal part in the metal of your choice. Another key advantage of the Project 3500 is that we use melt-away wax support. So all 3D printers need some sort of support structure around the part as it's being printed to hold it up. And the MJP technology from 3D Systems uses a very straightforward wax material to hold the part up as it's being printed. And so after the print is done, the post-processing is very easy. You simply take the parts out of the printer, you put them in an oven where you heat to a temperature that will melt the wax away, and you can see this little GIF that's playing here, how the wax simply melts off the parts. You do a little bit of cleaning by hand after that, and your parts are ready to go. So there's no caustic chemicals needed. There's no high-pressure power washing that you need to do, which requires special hookups and can even damage the parts as you're cleaning them. So smaller features will survive and won't be broken off as you're doing the post-processing because the wax is just melting away. So it's a really convenient way to get to the parts that you need very quickly. And especially if you're printing more than just a few parts at a time, it's very fast to put these parts in an oven, walk away. You're not having to do anything. The wax is simply melting off while you're off doing other things. So you're not spending your time manually cleaning the parts off of the Project 3500, which is a big advantage over some of the other technologies that are out there. And the Project 3500 is easy to own. It's easy to operate. We offer a 5-year print head warranty on the Project 3500, and that goes to show the durability of the print heads on this machine. They're far more durable than a lot of the other systems on the market. We back that up with the 5-year warranty. Project 3500s are known for their efficient material use. The support that we print in the wax material is not solid. There's actually some air in that support, so we're not actually using that much support material as we're printing parts. So you get more efficient material use out of this system. And it's easy to use because you can manage and monitor prints on your iPhone or your iPad or an Android phone via the free apps that we make available with the printer. So in summary, why choose the Project 3500? It's because you get superior quality functional plastic parts quickly. They're high resolution with sharp edges, crisp details, and smooth surfaces. Again, it's not just about the look and the aesthetics. It has functional benefits as well. Parts release from molds more easily when you've got smooth surfaces. It's an intuitive and easy-to-use system that you can set up in your office. And having one of these printers means that you can test more ideas faster, very economically. All right, so let me hand it back to Ray and Frank, and they can talk about the results from the 3 example applications that we were talking about earlier.
Thanks, Tom. Just a quick summary. The real feature to the high temperature, the LCP project that we worked on, it was part of a package of 8 plastic parts, and this particular project happened to occur in parallel with another very similar development program that was going on at our customer. About halfway into the initial project, we approached our customer and said, listen, we've got these capabilities, and we informed them about them and said, what do you think? And the customer decided at that point, given the amount in which we were able to reduce the development cycle, they said, you know what, let's work up and basically another version of the same product. The first project had been launched. We're about 6 weeks into a 16-week project, part of which required traditional metal injection mold single cavity tooling, and we were underway with that project. Using the 3D printed tooling process, we undertook a second related project, and actually within a 4-week period went from an idea to fully developed 3D models, as well as functioning prototypes in metal and plastic, a total of about 11 parts in 4 weeks from ground zero to functioning prototypes, and actually came in ahead of the project that had launched many weeks earlier. So this really was the capstone test case for us to prove that, hey, there is something here. This does work. The elastomer project, again, as Frank mentioned, the number of iterations that our customers are able to do in the materials of choice is so important. It really allows that next level of being able to evaluate, are we on the right track, does it work? The thing we didn't bring up about this, this is a customer-facing part. This had to meet cosmetic requirements, and it did. Now, we didn't do any texturing to the mold. We used as-printed surfaces, but we were able to control the molding. We didn't get any jetting during injection. There was no sink. We mold parts without flash. It's not like we have to injection mold these and then carve them out later. They're out of the mold complete. The insert molded contact on the bottom there was a chance for us to bring what we do. We're metal and plastic guys, and being able to do all of that in-house and very fast for our customer gave them a single source for both materials. We got it done quick and ultimately got them into production very quickly. So printed tooling is a game changer. It matters to our engineers. It compresses the development time dramatically, and just pulls in schedules and makes things happen faster in real-world materials. So it's been a huge benefit for our customers, and we're excited about taking it to the next level.
I just wanted to add one thing in. You were talking about the cleaning on the parts. We routinely will print models for like the injection molded parts we're doing. We will actually print the contacts into the mold at like 0.15 millimeters thick. Fairly involved, fairly large contacts, and they'll survive the cleaning, and we could bring them out and actually get a little flex on them and everything else. The cleaning on these is a huge difference. You don't damage what you printed. So you could do very fine, very delicate parts in here.
That wraps up the presentation, and so now we're going to move on to our Q&A session. And with that, I'm going to introduce John Paul Velasco. He is one of my colleagues at 3D Systems, and he's going to start reading off some of your questions, and then Ray, Frank, or myself will do our best to answer those questions. JP?
Good morning, everyone. Thank you guys again for being here. We're going to start going through some questions. Do you have experience using mold release agents to assist in part removal?
Yes. We treat these pretty much the same as any other mold, all right? The way we make them is unique. The way that you inject the parts and remove the parts isn't, all right? If you don't make compensation for these, you just produce the mold differently, and after that you pretty much treat it the same as far as clamping it, injecting it, removing the parts. We don't use automatic ejectors or anything. We take them off a hand because usually our volumes are so low. But anything you would do with a normal mold, you do with these, and mold release is part of that.
Thank you so much. So we've gotten a couple questions on post-processing these parts. If you could go into a little detail about the post-processing of the tooling.
Really, aside from we take the wax off, and we've done a couple other things. We're currently working with 3D Systems right now on formalizing the secondary steps. Basically, what the post-processing does is it gives us a little extra life. We haven't found a part yet that we weren't able to at least get a few samples in an as-printed condition. So that's, the good news here is that, with the machine, some knowledge of injection molding and tooling, you can produce a mold that will get you a part.
Great, thank you. So we have another question. We've actually gotten a few on the limitations of materials. I think you covered that a little bit, but if you go into detail a little more.
The product, in the material that the parts are molded from, any material that we will mold in production, we will mold in these printed molds. Polycarbs, LCPs, elastomers, nylon, high-impact polystyrene, polypro. If we use it in production, we will mold it in these printed molds. There's no limitations. Like I say, it's basically a mold that we use a different manufacturing process to produce. All right, it's not like there's limitations and all we could do is, shoot the coldest material we could find. We put material in there. Actually, the highest we've ever done into these molds was 670 degrees. And we ran several parts, about 2-3 dozen parts through that mold with no apparent changes, okay? This material will take the heat if you treat it properly, but we don't make exceptions for this process in the part. The parts are, as they would be in production, exactly the same material, exactly the same tolerance.
And that includes filled and flame retardant materials as well.
Correct.
So we haven't had an issue with high glass loading or anything like that.
No, we shoot, actually the LCP part, that was a 30% glass.
We've done glass-filled polyesters, PBTs. We've done Ryton, PPS.
Great. Thanks so much. So we have another question on cooling lines and whether or not they help or benefit the design at all.
We don't use them. Okay, generally these are a lower volume, and like I said before, what you're going to find with this material is it's just totally neutral. All right, even if you ran cooling lines through it, this material does not like to transfer heat. So unless you had the lines almost immediately in contact with the part, they would do nothing. We've never made a mold that had cooling lines in it.
So we have another question. One of the many problems with prototyping with injection molding is the high cost of the molds, which severely limits the number of iterations possible. How does 3D printing mold affect the cost of the process? I think they're trying to get some more specific actually how much time and cost it saves.
Well, I mean, the cost is considerably less. It's part specific. It's hard to give just a hard and fast answer. Considerably less. We do hundreds of these parts, so there's a benefit to it. Time-wise, I mean, it's part specific. It's how much the customer needs, but you can see some of these parts we were turning in a day, 2 days. We've turned some pretty complicated polycarb parts in 2 days. There's really no comparison in the time it takes to get to where you want to go using this.
To put a finer point on the pricing, the cost-wise, again, the majority of the parts that we've done have fallen within the range that Frank shared. That's 6 to 8 inches long. You generally, smaller parts are probably in the $1,800 range, for a tool and a few parts. We've had them run up to, a few $1,000s for much bigger, much more complex parts. Being guys that we're tooling centric, so one of the things we'll do too is there are instances where we'll 3D print the mold and there might be features that we'll use metal for a core pin, a through hole, or something like that. So, we've also done some hybrid type things as well that can help us get some features and functionality very quickly.
Great, thank you. So the next question is, if the volumes for this process are so low, why wouldn't I just print the prototypes on a 3D printer?
If you could print LCP or polycarb, it'd be a real good idea. Okay, if you can't print elastomers, you can't print LCPs, these parts, I could print parts too and get them real quick. You won't get them out of material you want to use in production. I mean, it's not it's not an apples-to-apples comparison. These aren't parts to look at and hand around the table. These are fully functional production equivalents.
Yeah, and that can't be emphasized enough. I saw a few other questions about how long the parts last.
These aren't touchy. These are production parts.
Great, thank you. So we have one more question on if you use a metal insert for the sprue, or if you have you ever done this before?
We've done inserts.
For the sprue? I'm sorry, was that?
Oh, for the sprue, that depends on the part. When I go into higher volumes, depending how we're going to clamp up the mold, sometimes I will. Generally, I just run right into the plastic. If I know I'm going to be running more parts or I'm clamping differently, I'll go to a metal insert for the sprue. Generally, I don't. It just depends. It's part specific. Sometimes we use them, sometimes we don't. Normally, we do not. So there's no real hard and fast rule.
Yeah. Great, thank you. I'm sorry, I'm still reading through all the questions that you guys want. Ray and the rest of the BuyLink, do you guys see any ones particularly that pop out to you guys? Can you flag them in red so we can read them?
And there was one question on what type of material we're using for the molds, but I think Tom already addressed that. We use the X. I think the crystal would actually work too, but it's not as durable, it's not as strong as the X.
There was a good question out there too. Are we interested in metal printing? No question. We have a few ideas up our sleeves and hope to be pursuing that soon and perhaps have another webinar at some point in the future.
And let me also address that from the 3D Systems view. So when we talk about metal printing, there are broadly two ways to get a metal part from a 3D printer. One is the direct way, which is what we call direct metal printing, pretty obviously. And these are systems that we offer. They're called the ProX 100, 200, and 300. And these are production level machines that melt powders of various alloys into finished metal parts directly. And you can print in stainless steel, aluminum, cobalt chrome, titanium, a whole variety of different metal alloys that you can print directly in with those systems. There is also an indirect metal printing method which uses a version of the ProJet 3500 that prints wax sacrificial patterns where you print the part in a wax material, and then you use that to then make a casting, just as would be done with a traditional wax pattern that any foundry can do.
Great. We have another question that we saw is what surface finish can be achieved with these molds?
We don't polish them. Okay, we haven't tried that yet. We've been looking into it a little, but the parts, appearance-wise, are very good. I don't have a class of the finish, but they're definitely not objectionable. They look very nice. Couldn't really classify it for you. The one part we were talking about, I mean, that was an appearance part. It was on the outside of a product, had the logo cast right into it and everything else. So they look very good. I couldn't give you a class on the finish. It's not a mirror. I mean, you're not going to use it for a lens or anything else, but they look very good.
We print the tooling at a fairly high resolution. The net parts that come out of it look to have a very fine EDM finish to it. But again, it's a very even surface to it. Doesn't impact ejection, anything like that. So there was a good question we had with regard to insert molding, and a question about the thermal transfer between the plastic, the injection molded plastic, and the metal. We deal with that all the time. We're insert molders. It's what we see. We can run mold flows with and without inserts. with the printed tooling, it's a little different. There isn't exactly a database out there that can, help us determine how, specifically the plastic reacts within the printed tooling. But what we have seen is, hey, metal when combined with plastic and insert molding, it does act as a heat sink. In the examples we've had, the metal is usually very, very thin, so it hits equilibrium real quick. And typically, we know enough to build in mechanical ways of bonding the metal to the plastic. So I'm not sure exactly where the question was headed, but we're not seeing sink issues that we're not able to control. We don't have pull-out force issues. It performs as we expect it to for an insert molded part.
Exactly. Whatever your expectations would be out of a metal tool, besides polish, I mean, if you're doing lenses or something, you should see exactly the same thing from these parts.
Great, thank you. So I think we have time for maybe one or two more questions. So the next question we have is, are you manufacturing medical devices or short-term contact devices using this process?
We manufacture tooling to make the prototype parts for them. We're not really making any production. The machine is capable of it, but no, we're not making any production parts off that table currently.
As a company, all of the parts that we've done in prototype for pre-production have since been tooled up for high-volume manufacturing. So, ultimately we are producing those parts in high-volume manufacturing, but we, as Frank mentioned, what we're doing in the prototype or the pre-prototype phase here is for development and test purposes. It's not, they're not going directly to market with those parts. It's part of their development process.
Great. Tom, do you see maybe one last question you want to have asked?
There are so many.
I know.
Let me see.
Like I say, I think the key point to the real strength to these is how quickly you could get a part that meets all the specifications, all the requirements of a production part as far as material tolerance, performance, everything else, how quickly you could turn those. You're only turning a couple of them. It's not like you're going to go into production, but if you could reduce your testing cycle from months to weeks, that's a huge thing. These molds aren't driven by cost. They're driven by the speed that we could produce them at. Cost generally isn't the driver. I mean, usually they're less expensive, but that really isn't what we've seen. People enjoy that, but that's not the driver for buying them. The driver has been how quickly you could get to where you need to go.
So I do see a few questions about medical parts or industry-specific parts. And Frank or Ray, do you want to talk about that?
I don't necessarily understand the question. I mean, the tooling isn't industry-specific. To us, a part is a part, basically. At least in this case, I don't understand the question.
So the parts that you can shoot into these tools and the materials that you can run, they are production-level materials, and the parts that come out are identical to the production parts that would be made in the metal.
They are production equivalent parts. Okay, we don't make exceptions because of how we made them. We just make the part that was required considerably faster. All right, we use the production material. They can go in. We've done verification parts for medical devices out of these tools. Okay, they're exactly right.
So we have another question on overmolding. Oh, sorry.
I see a question on ITAR work. Yes, we do ITAR work, just to mention it.
Mm-hmm.
Let's finish up on that question about overmolding.
Yeah, so there was a question if you guys have ever tried overmolding and how successful was it, if you go into a little detail about that.
We've tried it. We don't get a lot of call for it, I guess, in this.
Well, we've overmolded Teflon tubing.
Yes.
We've put features. We've done that. We've overmolded springs. We've done a lot of different materials.
Matter of fact, we've overmolded the tubing.
Yeah.
Yeah, there's a lot. Everything is, some of these it's hard to give.
Fiber optic cable. We've overmolded fiber optics.
Yeah. So yeah, we can. Basically anything you would do in a metal mold within reason, you could do with these. Obviously threads are a little different, things like that, but what you have to look at this as a different tool to produce the mold, okay? Instead of going into a milling machine, you're going into a printer. You're still getting the mold, okay? It's a real mold. It doesn't have all the same characteristics as the aluminum or the steel, but it's a real mold. Whatever you would expect you could do in a metal mold, you should be able to do this within reason. I mean, if we get a part that's 6 or 8 inches in diameter, we won't. We'll go into metal for that just because of area and clamping. It's not for every part.
And we selected the machine that we did primarily because the table size, the build size is consistent with what we do internally. So that just kind of falls within the size range of what we normally get involved in.
Great. Well, we're at the top of the hour, so in the interest of everyone's time, we're going to wrap up now. So again, I'd like to thank Ray and Frank and the whole BuyLink team, as well as my colleague JP, and we have a few other folks from 3D Systems on the line. I want to thank everybody for spending the time here with us today. Hopefully you found this interesting and enlightening. Again, thanks everyone. We hope you enjoyed. Have a great day.